So, on to the unit circle. The unit circle is a visual representation of angles, degrees, and radians, and their exact values of cosine and sine. I usually use radians, by the way. The circle is derived from special triangles mentioned earlier, 30, 60, 90, and 45, 45, 90, assuming that the hypotenuse is length 1. So, obviously, each one of these lines is a radii, and they're all a length of 1. So if we look at this, it looks kind of complicated. Pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3. And if you want to memorize it that way, you can. I would suggest you do not spend time on the test deriving the unit circle from the special triangles, although that is more academic. There is a little trick to this. So if we drew these out, so this is our 30, 60, 90, our 45, 45, 90, and again our 30, 60, 90, but coming from the 60 degree angle, there's kind of a cheating way of doing this. For counting to, or for finding the radian values, so the angles, just count to 12. So there's, this would be 0 pi over 6, so every 30 degree angle, so 0 pi over 6, 2 pi over, or 1 pi, 0 pi over 6, 1 pi over 6, 2 pi over 6, all axes count for both 45 and 90 degree angles, so this would be 3 pi over 6, and so forth, until we get all the way around, and then that would be 12 pi over 6, which, if you simplify all these, that would become 2 pi. And 2 pi over 6 would be pi over 3. So we'd end up getting the unit circle as we see it generally in pictures. Then for the pi over 4s, you just count the 45 degree angles. So again, we count all the axes both times. So we get 0 pi over 4, 1 pi over 4, 2 pi over 4, 3 pi over 4, all the way around until you get to 8 pi over 4, which again simplifies to 2 pi. The reason why we count the axes both times, you can get to 90 degrees, or pi over 2, via 45 and 45, or with 30 plus 30 plus 30 equaling 90. So the axes we count for both. And that's how you get the radian values. For the cosine and sine values, there's a trick to it. You count to 3 down, so 1, 2, 3. And then you count back up. 1, put the comma, 2, 3. Next, we're going to square root everything. So root, 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 root. And lastly, we put everything over 2. So, the square root of 1, that's what this is. I apologize, my handwriting's really bad. But the square root of 1 is obviously just 1, so this would be 1/2 root 3 over 2, this would be root 2 over 2, root 2 over 2, this would be root 3 over 2, and then again, square root of 1 is just 1. So that is what we'd receive, and if we look back at our unit circle, we see that that's what we should have. 1/2 root 3 over 2, root 2 over 2, root 2 over 2, root 3 over 2, 1/2. So that was an easy way for us to create the cosine and sine. To create the other cosines and sines, you just reflect over an axis. So if we reflected here, so this root 3 over 2 would come to be the first one here. Root 2 over 2, again, we reflect over the y-axis, so it's right there. 1/2, still the first term because we reflected over the y-axis. And you can do that with the x-axis too. 1/2, 1/2. Root 2 over 2, root 2 over 2, root 3 over 2, root 3 over 2. The only thing you have to account for is quadrant signs still are in effect. So this is positive, positive, negative, positive, negative, negative, positive, negative for the x and y values. Also remember that the radius is 1. So if we look at the actual axes, the x and y axes, This is 1 over 0 up and down, 0 over 1 up, to the left 1, and down 1. So that's how you deal with the axes. So there are tricks to this. Again, count to 12 for all the 30-degree angles, pi over 6, 2 pi over 6, 3 over pi over 6, 4, 5, 6, 7, 8, 9, 10, 11, 12, and that simplifies down to 2 pi, which is what we need to end up with over here. And we could do that with 45-degree angles as well. 0 over 4, 1 pi over 4, 2, 3, 4, 5, 6, 7, 8. And 8 pi over 4 is 2 pi. So that would be my suggestion in memorizing this. But if you want to memorize it with the simplified forms, be my guest. So for identities, there's really, you could just understand that these are true, and that's fine if you can recognize a lot of them. Some of them are going to be too complicated, but like ones like this, you may just understand that is how trig operates. But aside from that, you really just need to sit down and memorize these, and there's no real trick to it, and that's unfortunate, but that is the way that it is. But yeah, there's reciprocal identities, Pythagorean identities, and you'll notice that these are kind of like the a squared plus b squared equals c squared, Pythagorean. We've got cofunction identities, even odds. So you can note these. Some of these have plus minus, and they do change. So that this is a point of confusion for some people. Like, so if you have tangent u plus or minus v, take note that the top one is plus or minus still, but the bottom part of the formula is minus plus. So the sign switches. Be careful of this. The sign is based on the quadrant. So if we look at a over 2, they're talking about these signs right here. So take note of that. And then the domain and ranges. So where this is kind of coming from is like you can't take like tangent when the denominator is 0, right? That will not generate a result because you can't divide by 0. So that's where like some of this stuff is coming from. So just understand what's possible and not possible when you're looking at the function domain and ranges. I can't stress this enough. These trig identities, you don't just need to like be able to recall them if you really have to think about it. I suggest that you get to the point where these are second nature, because they're going to ask you to manipulate these trig equations, and they're going to expect you to do pretty complex operations and do them very quickly. So if you're not very well versed in these and you have to think about them for a while, you're going to waste a lot of time on the praxis. Law of sines and cosines. Really what I want to get at between the law of cosines and sines versus SOHCAHTOA and Pythagorean theorem, these are the same thing, except SOHCAHTOA and Pythagorean theorem are easier because the triangle is at 90 degrees. So those formulas are derived from law of sines and cosines. So these really aren't that strange of a concept. They're just more versatile in the types of triangles they can address. And then, yeah, just take note of where the capital letters and lowercase letters are when you're taking a look at these formulas. And again, SOHCAHTOA and Pythagorean theorem, these are only for 90-degree triangles. De Moivre's theorem, this is on your cheat sheet, and just talking about the cheat sheet in general, I don't suggest you use it. Sometimes they won't give it to you, and they won't know what to do, and you have to take the test anyways. But even if you do have access to it via like a question mark button or whatever on the praxis, it still takes time to click it. And my perception is if you're having to go and look at that cheat sheet, you probably aren't very fluid at that stuff anyways. So memorize it, practice it, make it so that you don't have to spend the time going back to that cheat sheet and looking at it. Polar coordinates. Polar coordinates, so these confuse people sometimes. This is just a different way of expressing where you are. I mean, that's what a coordinate is. So they're saying that the distance away from the origin is a radii, so that's r. And where this line actually is, we can just state that by looking at the angle. So we could say r at 90 degrees. Again, I like radians, so you probably do, but yeah, and then that would be up here. So just a different mindset on how to get to a point when we're thinking about the axes. But if you do need to convert back, this is how you do so. So r sine theta is equal to y, r cosine theta is equal to x, and then you can move back to the coordinates that you're used to seeing.